Good morning, students. So in this session we are going to start chapter number 1, relation and function. In this chapter we are going to discuss the relation, function, what is domain, codomain, range. This everything we have already studied in class 11, and different types of function, their graphs, right? So now we are going to understand the term relation in mathematics, which have been used to derive the meaning of relation, according to which the two objects or the quantities which are related in recognizable connection of link between the two objects or quantity. For example, if I take a set of students of class 12 and the set of students of class 11 of the same school. So here we are defining a relation from set A to set B, right? So in this chapter, we'll study the different types of relation, function, composition, invertible functions and binary operation. So first we'll start with relation. So definition says, let A and B be a two non-empty set. Any subset of A cross B is called relation from A to B. If we denote relation from A to B by S, then it is written as S A to B, and AS, that is the relation, is a subset of Cartesian product of A and B. Next is empty set. What is empty set? If the relation is null set and it is a subset of A cross B, then S is called an empty relation from A to B. Next is universal relation. Universal relation means the relation which we are defining on the two set A and B, and the two set is non-empty. All the elements of that relation is equal to the Cartesian product of A and B, then S is called the universal relation from A to B. Now next is relation in set A. So let A be a non-empty set. A subset of A cross A is called a relation S on A. What is empty relation? Empty relation is that it is a null set, right? It is a null set for A cross A. Two set, Cartesian product of the set with itself. S is called a universal relation in the set A. Universal relation, if S, that is the relation, is A cross A, then S is called a universal relation. Then the set A, in the set A, if S belongs, if order pair x comma y is belonging to set S, then it is denoted by S is relation with Y. Next is reflexive relation. Reflexive relation, if S is the relation in the set A and A is relation with A, that is for every small a is belonging to the set A, right? Order pair A comma A belongs to S, for every A belong to A, then we say that S is reflexive relation in A. Next is symmetric relation. Symmetric relation is if S is defined as the relation in the set A and A is relation with B, as implies B relation with set A, element A, and A and B, they are the order pair of the relation of S, implies B comma A also belong to set S. For every A comma B that is belonging to A, we say that S is symmetry. Transitive relation. If we define S as a relation in the set A and A is an element of set A, is relation with B, and B is the relation with C, implies A has a relation with C. That is, for every A comma B belongs to S and B comma C belongs to S, implies A comma C also belongs to S for every A comma B belongs to A. Equivalence relation. If a relation S in the set A is reflexive, symmetric and transitive, then we can say that it is a equivalence relation in A. If S is equivalence relation for x comma y belongs to S, then we write with a notation x is equivalent to y. What is antisymmetric relation? Antisymmetric relation is that if S is a relation in the set A and if A, small a, as a relation with B and B is relation with A, implies A equal to B, for every A comma B belongs to A, then S is said to be antisymmetric relation. So now we are going to start the exercise sum based on finding the reflexive symmetry or transitivity. Determine which of the following relation is symmetric, reflexive or transitive. A equal to 1, 2, 3 up to 10. S is a relation which is defined of the form x comma y equal to 2x. So here S equal to is a relation x comma y equal to 2x is a relation on A 1, 2, 3 up to 10. So we define that if I take x equal to 1, we get y 2. So a relation is of the order form 1, 2, 2, 4, 3, 6, 4, 8, 8, 5, 10. Now, we'll prove for reflexive that 1 comma 1 according to the definition A comma A belongs to S. For every A belongs to A, then we say that it is a reflexive. So we take here 1 comma 1, but it is not in the relation, right? So it is not reflexive. Now if I take 1 comma 2 be an order pair which belongs to the set S, but 2 comma 1 is not in the set S, therefore it is not symmetric. For transitive we take a 3 set, 1 comma 2 belongs to S, 2 comma 4 belongs to S, but 1 comma 4 is not in the S, therefore it is not transitive. Next question is A is a set whose elements are 1, 2, 3, 4, 5, S x comma y and y divides x, right? So here the relation is given of the order form where y divides x is a relation on A whose elements are 1, 2, 3 up to 5. So now x divides x, that is true for every x belongs to n, that is x comma x belongs to S. S is reflexive. Now 1 divides 2, that implies 2 comma 1 belongs to S, but 2 does not divide 1, so 1 comma 2 does not belongs to S, therefore it is not symmetric. Now if y divides x and z divides y, then z divides x. For every x comma y and z they are in the set of natural number, means x comma y is belonging to the relation, y comma z belongs to the relation, then x comma z belongs to S, but this is not true, therefore it is not transitive. Now the next topic is 1-1 function. 1-1 function is also called injection. So we define the 1-1 function as a function which assigns a different element of the domain with a different element of the codomain, then it is called a 1-1 function. In mathematically we can write it as if a function f is defined from A to B, be a function for every x comma x1 comma x2 belongs to A. But here x1 is not equal to x2 implies f of x1 is not equal to f of x2, then we say that the function is 1-1 function. Onto function means what? It is the range of function. If it is equal to the codomain of the function, then we say that it is a onto function. That is for every y belongs to B. If every y belongs to B, that does not exist x belongs to A such that y equal to f of x, then we say that f is not onto function, right? Or we can say if for every y belongs to B, there exists x belongs to A such that y equal to f of x, then f is onto function. The next is inverse function. So for inverse function, if the function is, we define a two function here, f that is running from A to B, and there exists a function g that is running from B to A, then composition of function g with f is identity function, or composite of function f with g is identity function. Then we say that g running from B to A is the inverse function of f running from A to B, and it is denoted by f inverse, right? And inverse function that is from g running from B to A of f from A to B is a then inverse function of f from A to B exists if and only if the function f defined from A to B is 1-1 and onto. Now next is if the function is defined from A to B and g is a function which is defined from B to C is 1-1 and onto, composition of g with f is from A to C and it is also 1-1 and onto, then the inverse composition g of composite with f inverse is f inverse composition with g inverse. Now the sums based on 1-1 and onto function, and that first question is if function f is defined from R to R, f of x equal to 5x plus 7, and we have to prove that it is 1, 1 or onto. So let us take two elements that is belonging to R. Then f of at point x1 is equal to f at point x2 is 5x1 plus 7 equal to 5x2 plus 7. x7 is cancelled, we get 5x1 equal to 5x2, x1 equal to x2, therefore f is 1, 1 function. Now for onto, let y belongs to R. Suppose that x belongs to R, y equal to f of x is 5x plus 7. So from here we get the value of x as y minus 7 upon 5. So for every y belongs to R, there exists x equal to y minus 7 upon 5, which belongs to R, such that f of x, in place of x in the function you write y minus 7 upon 5. So we get 5 into y minus 7 upon 5 plus 7 is y. So we can say that the function f is onto function. Next question is, if the function is defined from R to R, f of x equal to 2 minus 3x. So let us take x1 and x2 which belongs to R. F of f at point x1 is equal to f at point x2. So 2 minus 3x1 equal to 2 minus 3x2. Minus 3x1 equal to minus 3x2, x1 equal to x2, so f is 1, 1 function. Let y belongs to R. Suppose x belongs to R, y equal to f of x equal to 2 minus 3x. So x is what? It is 2 minus 5 upon 3. So for every y belongs to R, there exists x equal to y minus 2 minus 5 upon 3 is also in R, such that f of x equal to f of 2 minus 5 upon 3. Replace the f x in the function by 2 minus 5 upon 3, so we get y. Next question is, if the function is defined from R to open interval minus 1 to 1, f of x equal to x upon 1 plus modulus of x. So we'll consider the two cases where the x1 and x2. First we'll choose x1 and x2 which are belonging to R, and then we'll consider the two cases where x1 and x2 are greater than 0, and second case is when it is less than 0, third case when one is less than 0, other is greater than 0, and the fourth case is when the first is greater than 0, other is less than 0. So first case is when both the x1 and x2 are greater or equal to 0. So f of x1 equal to f of x2, x1 upon 1 plus mod of x1 equal to x2 upon 1 plus mod of x2. So x1 upon, because it's greater, we'll remove the modulus sign, cross multiply, so we get x1 equal to x2. Second case when both are negative. So here in the place of modulus we will write minus of x1, here it is x2. Again cross multiply, simplify that, we get x1 equal to x2. Case 3 is when x1 is less than 0 and x2 is greater than 0. So if it is less than 0, that means f of x1 is less than 0, and if it is greater than 0, then f of x2 is greater than 0. So x1 is not equal to x2, therefore it is not 1, 1 function. Similarly, we can prove for x1 greater than equal to 0 and x2 less than 0. Again you will get that it is not equal to 0. So 1, 2, 3, it is clear that f is 1, 1 function. Now for onto, let y belongs to open interval minus 1 to 1. Suppose that for x belongs to R, y equal to f of x equal to x upon 1 plus mod of x. We have when y is greater equal to 0, then y equal to x upon 1 plus modulus of x, y equal to, because here x is greater equal to 0, so we'll remove the modulus sign, cross multiply, we get x equal to y upon 1 minus y. So for every y greater equal to 0, there exists x equal to y upon 1 minus y belongs to R, such that f of x equal to f of y upon 1 minus y. So y upon 1 minus y upon 1 plus y upon 1 minus y, you get it, it's a y. Second case is when y is less than 0 and x is less than 0, right? So in the place of modulus, we'll write minus x, again cross multiply. So for every y less than 0, there exists x equal to y upon 1 plus y, such that f of x equal to f of y upon 1 plus y. In place of x, write y upon 1 plus y and simplify, we get y. So from this, it is clear that for every x belongs to y belongs to open interval minus 1 to 1, it is a onto function.